the, the understanding of potential revisions to the PG Asphalt Binder Specifications. My name is Tim Aschenbrenner. I'm with FHWA's Office of Infrastructure Pavement Materials team. I'm an asphalt pavement and materials engineer, also working with quality assurance. We have a cooperative agreement with the University of Nevada, Reno. It's on development and deployment of innovative asphalt pavement technologies. Really, to put it succinctly, it's about implementation. We're trying to advance implementation of various innovative strategies around the country. Today is the PG Binder Specification, but we have about 15 or so different tasks we work on simultaneously. Mike, if you could go ahead and share a slide. But our presenter today is going to be Mike Anderson from the Asphalt Institute. He'll have about a 45 or so minute presentation, plus or minus. That'll be followed by Q&A. Since we have about an hour and 50 or hour and a half total, we will have plenty of time for Q&A. So be sure to enter your questions in the chat pod as they come up. I'd ask everybody if you could keep your microphones muted throughout the presentation, and then we'll cover questions in the chat box. I'll go through the questions, and then Mike will answer them as time permits. Usually we get through all the questions, but in case we don't, we will reach back out to each of you separately to answer your question. And the webinar is being recorded so we can make it available, and it'll be available after the event. Usually takes a couple weeks because we have to go through various processes. So with that in mind, let me turn it over to Mike Anderson from the Asphalt Institute for today's presentation.
Okay, thanks, Tim. Hopefully everybody can see the screen and can hear me okay.
Yes, so I can see the screen and hear. Very good.
Great. As Tim mentioned, this presentation is about understanding potential revisions to the PG Asphalt Binder Specifications. And where this comes from, and we'll talk about this as we get into the presentation a little bit further, has been some recent research, relatively recent research that's been completed through the National Cooperative Highway Research Program. And it's been on binders and specifically looking at intermediate temperature cracking and some issues, how that works within the binder specification and what some recommended changes are. And we'll talk a little bit about that. There's also a project that discusses binder aging and how that relates to mixture aging and what we see in the field. So we'll touch on that. I think we'll have some time in order to touch on those. Tim's gone through the introductory part. I will post the disclaimer. I'm not going to read all that for you, but just the standard disclaimers, and that it's a cooperative agreement. It's with Federal Highway Administration. U.S. government doesn't endorse products or manufacturers. And if we're referencing AASHTO and ASTM standards, understand that content, that's private voluntary standards, and compliance with them is not required under federal law. I think the rest of it should be pretty straightforward, but it's there if you want to read through that. First things first, really, as Tim mentioned, this is an implementation project. And it actually was born of some work that we did for the National Cooperative Highway Research Program that was also considered an implementation project. And it goes by the number of 20-44 PRIN 19, which is not a really convenient number, but basically the 20 series of numbers in NCHRP are kind of like special projects. And the PRIN 19 part means it started in 2019. And so thanks to that project and the panel and the program officers for their input on that. Also, really, because what we're doing is we're talking about implementation, This isn't research that we did or that the University of Nevada, Reno did, or even our team members, I don't think, did. So it's really just reporting on what those results were and trying to understand how they fit together with any potential changes we might be looking at in the PG binder specifications. So we really couldn't do this without the research teams, is what I'm getting at. So thanks to those folks, the research teams for 959, 960, and 961. And I'll talk a little bit about who those folks are. Thanks, of course, to this cooperative agreement that is looking at how do we deploy these technologies. And last but not least, certainly in my case, thanks to our member companies of the Asphalt Institute who make it possible for me to do work like this. So the three projects that we're going to touch on really, I think, fall into the category of binder aging, fatigue, and durability. So 959 was relating asphalt binder fatigue properties to asphalt mixture fatigue performance. 960 has got a really kind of a long title, but basically it's saying how do we address changes that have happened certainly in recent years in asphalt binder formulation and manufacture. How do we address those in the asphalt binder specification? And then 961, as I mentioned, was really about aging of the asphalt binder, short and long-term aging methods that reflect the aging that we see in asphalt mixtures. So before we get into those projects, I guess I want to step back briefly and cover some basics. And this is important to kind of set the stage for, okay, well, why are we doing some of these things and what do they mean and how do they influence the performance that we see on the road? Specifically, how are asphalt pavements affected by temperature and traffic loading? How does aging affect asphalt pavements? What distresses are we trying to minimize? And what do we want from an asphalt binder specification? These were all questions that they asked during the Strategic Highway Research Program as they were developing what was the PG Asphalt Binder Specification. And it's really the questions we ask today. How do we establish a specification that addresses the distresses that we want to be able to take a look at for asphalt pavements? So I'll touch on some of this, and some of it is admittedly a little basic probably for some of you all, but just it's a good review, I think. First, in high temperature behavior, what we're looking at, and there's, when this slide was first developed, it was developed, I remember, by Bob McGinnis back when we were doing training with the Federal Highway Administration after SHARP ended. And this was about in 1994, 1995. We had these classes and we were teaching, and we talked about rutting and depressions in an asphalt mixture. And we said, well, it depends on the asphalt binder, the mineral aggregate, and volumetric proportioning. And you see that sum in parentheses. What that means is that each of those has some role to play in what happens in rutting in a pavement. And we're talking about material rutting, not subgrade rutting or anything along those lines, which we don't control. But from an asphalt mixture standpoint, the asphalt binder has a role to play, the aggregate has a role to play, and the volumetric proportioning has a role to play. And we say that because it's important that you don't just rely on one of those factors to try and control your rutting. In other words, if I have a really good binder and I put it together with rounded aggregates and lots of natural sand and that sort of thing, and I'm putting it out on a high traffic volume roadway, it's probably not going to perform all that well, even though I've got a really good binder. By the converse, if I've got really good aggregates and it's a really strong aggregate structure, but I use too soft of a binder, it may not perform very well. And for volumetrics, what that basically means is what happens if I add too much asphalt to my mix? If I put in just pour asphalt into there, it's going to have bleeding and potentially rutting, regardless of the aggregate and the binder. So all those things kind of play a role that we're looking at. And that happens a lot with our distresses that we're interested in. And that's important to think about as you're establishing a specification. As far as low temperature cracking goes and low temperature asphalt pavement behavior, what we're interested in is cracking. And that's a case where if you get the temperature of the mix is dropping, you get internal stresses that develop in the mix that's caused by this temperature drop. And if your binder is too brittle for that environment or too stiff for that environment, then it can't relax the stress quickly enough and a crack develops. And then that happens as soon as the stresses exceed the strength overall, and you tend to get the transverse full width type of cracking. Now, in this kind of distress, it depends really very much on the asphalt binder itself and not as much on the other factors. A little bit on volumetric proportioning, but not as much on mineral aggregate. And the reason for that is the asphalt's the glue. That's the part that's really temperature sensitive. So when it changes temperature, that's the part that's shrinking. So even though you got two rocks that are stuck together with the glue in between them, as the temperature drops, the rocks don't change with temperature, but the glue does. And when that does and it shrinks, that's where your stresses build up. So it really depends very much on the asphalt binder itself. The other piece that we look at is durability cracking and what happens as an asphalt binder ages. So you've heard people talk about fatigue cracking. That's the type of cracking we get from loading, repeated loading. As cars and trucks pass over a pavement, it flexes, it relaxes. And the example I like to use when I'm giving tours in our laboratory is that's a lot like bending a paper clip. I don't know if you've ever done this, but I've done it before. Just when you're bored, you've got a paper clip, you straighten it out, and you just kind of bend it back and forth. Well, eventually it's going to break, but how quickly does it break? Well, it depends on how much I'm bending it back and forth. If I'm just bending it a little bit back and forth, it's probably going to last for a while. If I'm making big movements, it's probably going to break relatively quickly. And it's going to depend upon the paper clip strength itself. If I've got like a cheap paper clip, maybe it's going to break a little bit earlier than one that's a little bit better quality, made from a better quality. So those are what we look at for fatigue cracking. With aging, what happens is an asphalt pavement oxidizes, and it's a hydrocarbon, and it's like any of the rest of us. We age and we oxidize and we get stiffer and we become more brittle. And that's what happens with a mixture as well. We tend to see that in random wandering cracking. It can be longitudinal cracks. It also is these block type cracks that you see that form out there. And that's what we refer to as block cracking and durability cracking, although you can call it a lot of different things. It's going to depend upon the asphalt binder. It's going to depend upon the mineral aggregate a little bit. It's going to depend upon the volumetric proportioning. So all those things kind of have a role to play. But again, what's changing with oxygen is typically that asphalt binder, that hydrocarbon that we're working with. Now, there's a model that says that Matt Witzak and Dr. Mirza put together. This was back in 1995. That was a global aging model. And this excerpt is from their paper that they had back in 1995. I don't think I gave the reference to Ellie and Tim beforehand. So if you have an interest in that, I'll have to find that reference. But what they modeled was stiffness versus depth from the surface. And that's what this is an indication of here. Depth would go down on the y-axis, stiffness across on the x-axis. And the thing to note there is that if you are close to the surface, the stiffness is quite high. And as you get further down in, so this is about 100 millimeters or 4 inches down in the pavement surface, you can see the modulus here is about a quarter of what it is at the surface. So this is 20 gigapascals. Down here would be closer to maybe about 5 or 6 gigapascals. So 3 to 5 times difference that we're looking at there. So that tells us that a lot of the aging happens early at the top, near the top of the pavement surface. And that makes sense because as you built a pavement, you've got air voids in the pavement, air and water can get in through the top, and that air, that oxygen starts diffusing and it doesn't get as deep into the pavement structure itself. As a matter of fact, at some point, as you can kind of see from this graphic, it starts to really tail off where there's not much change here at all. And that's just telling us that the oxidation rate is changing quite a bit, and there's not as much free oxygen to be able to age the material. But at the surface, it's quite extensive, or can be quite extensive. So when Sharp was formed, this was the basis behind the PG specification. They had to address the question, what do we want from an asphalt binder specification? And there's a report out there, this is Sharp Report 9007, which was part of their strategic planning document, that said it was based on the premise that asphalt pavement performance is significantly influenced by the properties of the asphalt binder. However, they did not say that it was solely influenced by the properties of the asphalt binder. Again, it goes back to the mineral aggregates you're using and the volumetric properties. But they're also saying that you need to select an asphalt binder that has properties that meets minimum performance levels that's for the traffic and the environment in which it's expected to perform, both now and in the future. And they looked at several different distresses. They looked at permanent deformation or rutting. They looked at fatigue cracking, and they focused on thermal cracking. They did talk about moisture sensitivity and aging and adhesion, but they didn't really incorporate that within the specification. Aging was not really a distress, but it was seen as a factor in what would happen later with the distresses that you would see. So you wanted to be able to test the asphalt binder in a state that approximated what it would look like after a period of time in surface. Again, what you're really looking for in a binder specification is for the asphalt binder to minimize the contribution to distress. And we say minimize because, like I said, you're not going to completely take it away, even if you put in a great binder, if you don't do the other things well. So you want it to do its part, more or less. You want the binder to be able to hold up its end of the bargain. And in order to do that, you've got to have it meet certain minimum performance requirements. The other factors that you see there, I list those because those, as I mentioned earlier, excuse me, do contribute to distress. They can all contribute regardless of what the asphalt binder looks like. On the high temperature side, we've addressed this. This was not part of the NCHRP projects that we were talking about, but rather these were parts of the projects. This was something that came about earlier and has been in place. I think we had the master specification in place like in 2010, 2012, sometime in that time frame. But it looked at the multiple stress creep recovery, and that was to address rutting and the binder's contribution to rutting. And the way they did that was through this test. You've probably seen the masker. I'm not going to spend a lot of time on it, but basically what it is a creep and recovery test, and you're looking at what is the non-recoverable shear strain. So when you apply a load to it and you release it, how much of that load comes back? If it's elastic, if you got a lot of modified materials in it, if the temperature is lower relative to where the binder is going to perform, you're going to have less, it sounds funny to say less non-recoverable shear strain, less permanent shear strain, I guess, than if the temperature is at a higher temperature or you don't have as much of an elastic response like a modified material or something along those lines. So that's how we're addressing rutting within the binder specifications. And that's AASHTO M320 if you're interested in that. And that's one of the reasons why when I talk about PG binders, I say PG binder specifications, meaning that this is applicable in this case to both M320 and AASHTO M332. If you look at low temperature cracking and how it's addressed in mixed design, this report was done, it's been a while, NCHRP report 673, that was from NCHRP project 9-33. And it talked about how thermal cracking performance of asphalt mixtures were really most strongly influenced by the asphalt binder properties. So as long as you used an asphalt binder that was appropriate for the low temperature in which it was going to perform, then the expectation is you would have adequate thermal cracking performance. And we talked a little bit about this earlier, but that's just a note on the bottom that talks about how different the coefficient of thermal expansion is for asphalt binder compared to aggregates. It's why we worry so much about the asphalt binder properties at low temperature. And we use the BBR in order to characterize low temperature behavior. I don't think people are doing this currently, but there was at one point you could use the direct tension test and you could develop this thermal stress curve to look at critical cracking temperature. Interestingly enough, this kind of the concept of critical cracking temperature is similar to something we're going to talk about a little bit later on with the asphalt binder cracking device. And what temperature does that binder physically crack? And this was from modeling. That's a little bit more from a test itself. So let's look at the intermediate temperature parameters, because that's really what we're interested in for the most part with a couple of these projects. If we look at aging, durability, and fatigue cracking, how is that addressed in the SHARP reports? And this is SHARP report A367 that came out. And it talks about how they came up with the parameter that is currently in use in M320 and M332. And that's the G star times sine delta parameter. And they talk about it as being at the suggestion of the researchers, and in light of fatigue performance in field trials such as Zaka Wigmore, fatigue criterion was changed to reflect energy dissipated per load cycle. That dissipated energy is most appropriately calculated as G star times sine delta. So that's where they came about with the idea of using that in the specification. We'll talk a little bit more on that later. If you look at the data that you get out of SHARP report A388, which was looking at fatigue performance of mixtures, laboratory fatigue performance of asphalt mixtures. And you plotted their data. They did what they called I think it was called an 8x2 study, if I remember correctly, where they used 8 different core asphalt binders and they used 2 different aggregates. They actually used 2 different air void levels, 2 different strain levels. So a variety of conditions in there. But what you can see is that mixed fatigue life in the laboratory, generally speaking, responded to that G star times sine delta parameter. In other words, what we expect is that fatigue life is going to go down. You're going to have earlier cracking as the material gets harder. And that's what this is telling us more or less from these curves. They're not great. The R-squared values 0.57, 0.81. Depending on the strain level that you're looking at here and what your responses are. There's a lot of variability that occurs in mixed testing, particularly fatigue tests, because it's a cracking test. So some of that variability we expect to see, but in general, they felt like, okay, this justified what we were seeing behind using G star times sine delta. They further talked about you seeing something more than just a simple hardness shift that occurs during oxidative aging. It changes time temperature dependency as well, and that's reflected in the shape of the master curve and how that changes. And it further notes that the changes that occur are complicated. In general, strain to failure, deformation rate decreases with aging. The asphalt becomes more brittle and exhibits less strain tolerance with aging. So that's all out of the SHARP reports. So they recognize this during SHARP, that this sort of change happened. And one of the things that we've talked about in our lab whenever we're doing training is that for newer technicians in particular, it's easy to confuse stiffness and brittleness. Stiffness is just how hard the material is. Brittle is how likely it is to crack, or how it responds to strain and what kind of strain tolerance it has. So there's a difference between those two. Both things happen, not just stiffness increases as it ages, brittleness also increases. So let's talk about the research projects, 959 first, and then we'll touch on some others. This is this research project was done mainly by Don Christensen with Advanced Asphalt Technologies, NAMTRAN with NCAT. You can see the objectives up there. Basically, what they wanted to find was a practical implementable binder test that would be a significant indicator of mixture fatigue properties. You see the NCHRP report. I think that's also listed for you. that you can, I know it was in the reference list, so you can access that. That's a free PDF download if you're interested. Some of the key findings that they were looking at there, and I'm not going to read all this because it says it basically what I've said before, fatigue life is going to depend on a lot of different things. But what the focus is overall is how does the binder failure strain contribute and what happens to the fatigue performance? And if you boil that down and you just kind of highlight what that means, as the binder becomes stiffer, as G star increases, the fatigue life or resistance to fatigue damage decreases. And as the binder becomes more brittle, as the phase angle decreases, in other words, it starts behaving more like an elastic solid than a viscous liquid, then the resistance to fatigue damage decreases. So both of those things happen, and that happens with aging. And that is reflected somewhat in G star times sine delta, but we'll see what that looks like overall. What they suggested in their research was that for fatigue, that you should replace that G star times sine delta with the Glover-Rowe parameter. And that's determined at a frequency of 10 radians per second. And then they established a maximum allowable limit that's basically the same as what we have for G star times sine delta. Now, if you're not familiar with the Glover-Rowe parameter, it still uses G star, it still uses delta, but it uses them in a different way. And you can see the equation there. It's cosine delta squared over sine delta. It's hard to kind of get your head wrapped around that, what that means basically. But what it means in essence is that delta plays a bigger role in determining what that value is going to be than just what we see with G star times sine delta. And I'll explain here in the next slide what I mean by that. So if you are the graph on the left here, this is from research we did with an airfield study. And we looked at unaged material, PAV20, PAV40, and PAV80 materials. And the dots that you see up there, the white circles, pardon me, are equal conditions. So they're the same testing frequency, same temperature. This is called a black space diagram. We plot G star versus phase angle. It's a convenient way to look at both of those. What happens with aging at the same conditions is the material moves from the lower right to the upper left. So as it ages, it gets stiffer. So G star is going up and phase angle is going down. Okay, so that happens as the material gets stiffer. And you can see this is a fairly linear sort of a response overall as to how the binder ages from an unaged condition to a much more severely aged condition. And I illustrate that because I want to use that in looking at this graph on the right. So these are some 6422s, 7622s that we tested in our lab back in 2016. And we plotted this to take a look at, well, what does G star versus phase angle look like for these materials? And how do they compare with the specification? So first things first, if you take this orange line out for now, just ignore the orange line. Everything in 2016 was you had to be at or below that green line. Anything above that would fail G star sine delta of 5,000. Okay, so all this data meets the AASHTO M320 from back in 2016. This is the proposed line for Glover-Rowe parameter, this orange line that you see here. And you can see some differences here. First of all, anything above that is going to be a failure compared to where it was. So some materials that had previously passed might not pass with the Glover-Rowe, particularly as you get to higher stiffnesses and lower phase angle type of materials. This one is well out there, for instance. It passes easily, G star times sine delta. It would fail easily the Glover-Rowe parameter. The other thing to note about this is, as these are 76 minus 22s tested at 31 degrees C, if we test them at more appropriate climatic temperatures, like 25 degrees C, which would be for Kentucky about appropriate, we would expect the data to move up and into this group here. So it moves lower right to upper left. And it follows kind of a similar sort of a shape here. It's not quite the same, but it follows a similar shape to what we would see with aging. And I think, as I say, it moves in this direction. The other thing that you see is that the Glover row parameter provides us, I would say, a better defining line for our specification. As I move in this direction, I'm kind of approaching this limit obliquely. So as phase angle goes down, oddly enough, this line kind of goes up. The Glover row creates more of an angle where you're going to cross it right at a perpendicular. So rationally, from a specification standpoint, approaching a limit, passing it, it makes a little bit more sense potentially to do something like that. The other thing that they looked at in the 959 research was R value. Now, R value just defines for you the shape of the master curve. And they talked about that in the Sharp reports and how that changes with aging. Well, the calculation that Don uses in this, and this was from work that he did when he was with the Sharp program, the Penn State research team, was to calculate R value. And this is using BBR data. So he uses this R calculation with a log of stiffness divided by 3,000 and the log of 1 minus the M value. So basically, you're taking the BBR creep stiffness at 60 seconds, the M value at 60 seconds, you're plugging that in for S and M, and you're calculating R. So from that standpoint, a pretty straightforward calculation. Now, this is how you would use the BBR data. You'd probably just need, eventually to get a new printout from Canon or ATS. In this case, this is a Canon printout, I guess, or any other manufacturer that's out there. And you would just basically add a column that would calculate R value for you based on that BBR stiffness and M value. The equation just is shown here, and you can get this parameter, this value that's there. There's some caveats to that. First of all, what you're doing here in this, using this 3,000 number, is you're assuming a glassy modulus. And that's an assumption that may or may not be valid. It depends on the asphalt binders themselves. There's a lot of rheologists that'll tell you that it's not a fixed number. It's not so easy to say it's 3,000 in bending. If you're wondering why it's 3,000 and not what we typically think of as in 1,000 megapascals or 1 gigapascal, it's because we think 1 gigapascal is for shear. Bending is about 3 times that number. So that glassy modulus may or may not be applicable. It gives us an index, but again, it's based on some values that you have to make some assumptions in order to use it, and that is a bit of a negative. The other thing that they put together were a recommended change in temperatures. And you can see what these temperatures look like here. that basically, I'm looking ahead, sorry. Basically, they're saying instead of basing it on the average plus 4 degrees, it ought to be based on the low PG. So this is what your table looks like. They're recommended based just on the low PG grade. For some binders, it's not going to make a change. For others, it's going to make a bit more of a change. So generally speaking, if you're a 64 grade and you're a 64 minus 22 or a 64 minus 28, it's about the same intermediate temperature. So no changes there. If you're higher than a 64 grade, you're probably going to test at colder temperatures. If you're lower than a 64 grade, you're probably going to test at a little bit warmer temperatures. And in some cases, those impacts can be pretty big. Let's talk about 960 and the work that they did. And I'll summarize some of this with 959 a little bit later. So 960, big long title. It was done with J.P. Planche at Western Research Institute, Michael Oردani, Don Christensen was involved, Gail King, Carolina Rodesno with NCAT, and then a consultant statistician as well. And basically what this project was intended to do was to say, look, we recognize there might be some gaps and shortcomings in the specification that particularly is related to durability in the form of cracking and raveling. How do we address those in the specifications? There is not a published final report yet. The project is into a phase 3. There is a draft final report that will be published in conjunction with the phase 3 findings. What their work so far has identified is that they're recommending adding a parameter like delta TC to both AASHTO M320 and M332 that relates to the relaxation properties of unmodified binders and generally relates to the colloidal structure of the asphalt binder. I had to slow down because I always struggle with colloidal. That takes me a little bit. They also note that the use of delta TC alone can underestimate the performance of modified materials in some complex binders. And part of the reason for that is you're using a rheological parameter, a small stress, small strain parameter, which is what delta TC is telling you. And you're trying to see how does that relate to cracking, which is at a higher strain level. And polymers have a different strain tolerance, and polymer modified binders might have a different strain tolerance than an unmodified asphalt binder. So we want to be able to capture that somehow. What they further recommended was the use of the asphalt binder cracking device to help capture that strain tolerance and that strain tolerance of the materials. That's given an AASHTO T387. It uses the critical temperature at which the BBR stiffness at 60 seconds is equal to the specification value. We call that TCS. And then it uses the critical cracking temperature from the ABCD to create this new parameter that's called delta TF. And basically, that's just looking at the spread between what a rheological parameter tells us it ought to look like from a stress strain standpoint versus what it actually has in cracking from an actual cracking test, and what that difference in strain tolerance is. Generally speaking, if you get a broader range in delta TF, you've got more strain tolerance relative to its stiffness. So that's what that is telling us. Their recommended parameters, and again, this is still going through some vetting, is anything below -6 on delta TC is a fail. This is all at PAB 20, I should have said. Anything above -2 delta TC is an automatic pass. And in between those two is well, you got to do some more work just to see, is that relaxation gonna be a problem, or is the binder gonna have enough strain tolerance? And what that means is that's where you go to the ABCD. You use this asphalt binder cracking device. And basically what they're looking for there is a certain range of values that says that it's good enough that it can withstand that apparent poor relaxation, if you will. So the way we do that, the ABCD, this is given an AASHTO T387, is that it's heated, it's poured into a silicone mold that's got a strain gauge. We'll see a picture of this in just a minute. It's cooled at a constant rate. And then the sample cracks when a jump in the strain occurs, and that's where the critical cracking temperature is. You see the notes there about the cooling rate. And I know in CHRP 9-60 in their first phase and second phase, they were looking at a slightly different cooling rate than what is given there in T387. I think they might be going back just to the T387. So don't, even though I'm showing 20 and 10 versus 40 and 20 degrees C per hour, when the recommendations are all said and done, it might very well still be what T387 says. So don't hold on to that too tightly. This is what the ABCD looks like. We took these pictures up at Ohio DOT's Office of Materials Management. They had a device, and Eric Beal and his team were kind enough to invite us in to see this in operation. But on the left-hand side, this is the mold. You can see the gap with the strain gauge in here. We pour the sample in, it goes into a chamber here, and that's where the temperature starts dropping, and we can measure what that strain is. So we've got to think of this from starting here on the right-hand side. As it gets cooled down, it reaches a point where the crack occurs. That's when you see this jump in strain happen, and then you get this post-crack strain that occurs overall. That defines for us what that cracking temperature is, where that jump in strain occurs, okay? And it's that critical cracking temperature that we use with the TCS that we get from the bending beam rheometer in order to calculate this delta TF. So the way this is right now, given this is courtesy of the 960 folks and Western Research, is that anything in this region, again, this is -2 and higher. This is region 1, everything's okay. Anything in this region, region 2, which is -6 and lower, is going to fail. In between -2 and -6, there is a minimum delta TF required, and that changes. It's not just a minimum, it's across the board, but it gets a little bit more harsh, if you will, as you get lower and lower on that delta TF criteria, such that if you're above that in the 3 region, you pass, below that in the 4 region, you fail. Okay. So there are some challenges involved with this and how what the impacts are. One of the challenges with delta TC is it requires testing at 2 or sometimes 3 BBR temperatures. And this can be an operational challenge, particularly for user agencies that are used to just verifying the asphalt binder grade. Now, instead of just running a -12 for a 64 -22, now you got to run at -12 and -18, and potentially, depending on what the delta TC is, maybe at -24 or maybe at -6. So you could be running at multiple temperatures, and that can add to the challenge. This is an older slide. I don't know that the equipment cost is necessarily accurate anymore, but one of the things that we found early on is that if you're going to classify those materials that are in between -2 and -6, you need the ABCD device, and that's a new piece of equipment for a lot of people. 40 to 50,000. I mean, it's probably in the range of what you would spend for other binder equipment, but it's a new piece of equipment, and so you have to account for that certainly. And it's not, as I always tell people, it's not just a new piece of equipment. It's a new piece of equipment I've got to maintain and calibrate and make sure is in my quality management system, have students that are trained on it, etc. The other thing is you might need some additional PAV pans. If you're going to pour up those molds that you saw there, I think it's about 14 grams that is required per ABCD ring that you pour up, give or take. So you think about that, you're going to pour up 4 of those, that puts you at 56 grams of material. So you need 1+ pan of PAV just to have enough material to do the ABCD testing. So it's going to mean some additional aging that's going to be there as well. So how do we relate those two? They seem to be somewhat related. 959 was looking at fatigue cracking. 960 was looking at durability cracking. What's the relationship between those? Because those are both intermediate temperature. We want to look at what the specification objectives were for both of those, what they were trying to achieve within the research. Again, fatigue versus durability in the form of raveling and cracking. And to do that, we go back to the Sharp work and what they reported on. And the reference, if you remember correctly, we talked about the Zacher-Wigmore test road, asphalt test road. So this is reported in a paper from 1969. So 50+ years ago, 60, or not quite 60 years ago, but 55 years ago, something along those lines. My quick math isn't working for me. But it was reported by Zub and Skog in this 1969 paper. And this was a test road that was on US 101 in Santa Barbara County, California. They had 10 asphalt binders. They were 200 to 300 pin material. And why it was important was what you saw there in the reference we used earlier. That's what the Sharp researchers used as a reference for fatigue performance in suggesting we go with G-star times sine delta. What's highlighted on the map is where roughly Santa Barbara County, that's Santa Barbara County. I've not been able to identify where exactly the Zacher-Wigmore test road was. It was actually, my understanding was it was between 2 train stations that are no longer there. So this was, some years ago that they had these train stations, but it was a test road that more or less was between those 2 stations. But what was interesting about this test road, the 10 different binders they looked at and all that, and this climate, which is Southern California, so not really thermal cracking is not really what you're worried about so much. But they found fatigue cracking, and they said that was the most prevalent on the project, and it was related to the stiffness of the asphalt binder, the recovered binder consistency. But they also found a secondary distress that was most prevalent in the passing lane, so the lane that was less traveled, had less trafficking, and that was block cracking with raveling, and they found that was related to a gain in shear susceptibility during weathering or a drop in ductility during service life. In other words, as the material became more brittle, they saw more of this block cracking with raveling. So there actually were two distresses on that road. The sharp research mainly focused on fatigue cracking and perhaps thought that what they were hoping to capture with G-star sine delta would also capture the block cracking that they saw. So the specification that we've got now, G-star times sine delta, you can reference that back. May not be perfect as a parameter, but there is some referenceable information that suggests it is related to fatigue cracking. But there's not really anything that we had for durability or block cracking. So the research that's come out now is suggesting Glover Row instead of G-star sine delta, and a new parameter that they're suggesting for that durability. And that's either R value, which was from 959 research, or delta TC, which was from the 960 research, or another parameter that we've looked at and others that have been involved in this, Jeff Rowe, and I know ExxonMobil Imperial has been working this issue as well, where they're looking at phase angle at a critical G-star or at a certain G-star value. And they're all interrelated, and we'll see that here in just a minute. This is the relationship between R value and delta TC for a number of binders that we had done testing on. Those are shown in blue, the blue diamonds. But the orange circles you see there are from the Sharp A645 report. So this is data that was available. We just went back to it and found it and plotted the calculated R value versus delta TC. And because they use kind of the same data, there is a really good relationship, and you can see that there. And the other part is it sort of overlays. So whether we were talking about newer materials that we've tested or materials we tested back in the late 80s and early 90s, we see a bit of an overlay there, and there is a relationship that tells us that those two parameters are related. This is just what it looks like if you put them all together and you just said, what's the R square look like? In general, that's not too bad, you know, to look at that for all those different data sets that are there. You get a little bit of tail off and you could argue whether a linear fit is the right fit, but overall, it's not too bad. If you look at the requirements that they put into 960 based on that data, it would say that your absolute failure top end is 2.6 for R value. That's at a -6 delta TC. And basically anything above or below a 2.2 on R value would be acceptable. That yellow is kind of the middle area. If you look at the 959 research, they say the absolute top end is 2.5, which is actually about a delta TC of -5. And their other end, which they aren't as worried about, is a 1.5. That's a delta TC of about +4, which you'll see occasionally with some materials, but most materials are in value controlled, and so they're more negative than they are positive. So overlaying those two, that's kind of the region there. That little rectangle that you see here is kind of the region of overlap of performance where we would expect those two specifications, those two research projects and their recommendations to recommend that those materials are acceptable. If you start getting out here, these would be levels that the 959 might consider unacceptable, but 960 would say maybe is okay. That one, the 959 says is good, 960 says maybe. These, they both say are not very good. So there is some overlap between these data. One of the questions is, how does this work with modified materials? This is work from the 9-10 research that was led by Hussein Bahia and is reported in NCHRP report 459. And you can see there, what I did again was I did some data mining back from the data that we had. 12 different modification materials and processes that you see there, 14 different grades. It was quite extensive research that Hussein led on this effort. including some oxidized materials and polyethylene and ethylene vinyl acetate and SBR, SBS, that sort of thing. And they still get a pretty good relationship between R value and delta TC. So even though these are rheological parameters, they do have some relationship still between those two parameters. And again, I want to be clear, R value is calculated from BBR data. Delta TC is calculated from BBR data. So we expect there to be a good relationship. This wasn't a surprise necessarily, but we wanted to show how they were related, not that they were related. The other part is to look at delta TC versus both R value and versus this phase angle. So the phase angle is, we chose phase angle at a G star of 10 megapascals. That tends to be where people are coalescing around that kind of idea. And you can see this relationship. Again, it's a pretty decent relationship. We get a little squirrely as we get out towards the ends. But for materials that we are looking at here, generally speaking, if you have a lower phase angle at a given modulus value, in this case 10 megapascals, it's going to be correlated with less relaxation. And that's going to be correlated with this delta TC that we see here. This is the orange dots here are R value versus delta TC. And again, a good relationship there because they're using the same parameters that they're calculated off of. So let me touch on 961 briefly. I know we're getting a little shorter on time, so I'll try to go through this and then we'll pick it up from there on what all this means. This is looking at aging. And so this report is reported in 967, the report 967. Work done by Ray Bonnequist with Advanced Asphalt Technologies with Jeremy Adams at Western Research and Dave Anderson as a consultant. And basically they were looking at short-term and long-term aging of binders, the procedures we use and how they correlate with what we see in the mixture field. And basically the outcome of this was that they found that the RTFO that we've been using for some time, basically since Sharp and the PG system had come about, is really about as appropriate as we can get it. It reasonably correlates with the aging that we see, short-term aging that we see during production of asphalt mixtures. There's some challenges as you're using modified materials. We see some rolling out of bottles in some cases, and some of that is technique driven. So there's some guidance that's in there, but generally speaking, what they said was the RTFO seems to be doing a pretty good job. Now they didn't focus on the elevation changes. That was a different project, and that made its way into T240. So if we look at T240 now, you'll see that you're going to change the time based on elevation changes. That comes from a different research project, but it's not from this one where they talked about these changes. Oops, I went backwards, sorry. What they found from the PAV is that you can change the operating parameters of the PAV to reasonably simulate near surface aging after 10 years in surface. But to do that, it's going to require thinner films and higher temperatures potentially. So what they did in their research was they looked at how do you model that? And that was 20-hour aging, 2.1 megapascals, which is the standard pressure, but only using 12.5 grams instead of 50 grams. So what you've done in essence is you've cut the film thickness in that pan from 3.1 millimeters down to 0.8 millimeters. Okay, so it's a much thinner film and it allows oxygen to diffuse quicker into the asphalt film itself. They did calibrate the results to the properties of recovered binders from 26 LTPP sections. And what they found were they had cores between 8 and 16 years of service. And they were able to calibrate that to get this as far as what the PAV temperature would look like and what the aging would look like. So what they were careful to say is that if you're using RTFO, you really don't have to do any changes. If you're sticking with a 20-hour PAV, you really don't have to do any changes. But if you want a longer simulation, you could do the 40-hour PAV, but instead of doing the standard 40-hour PAV with 50 grams of asphalt binder in it, you use a 20-hour PAV with 12.5 grams of asphalt binder in it and slightly different temperatures. And their temperature profile you see here, which is basically to say If it could go as low as 85, which right now we're at 90 as a low end. It could go as high as 115, and right now we're at 110 on the high end. But for the most part, you see these are weather stations where that would be appropriate. You're way out on the edges here. So maybe one or two places, and that's all. Your 52/28s, 58/28s, 64/28s, 58/22s, those are the predominant one. Those are all going to be at 100 degrees C. 64/22, this is a little bit of change for people. It would be a 105. 52/34 would be a 95. 64/10, 70 minus 16 would be 110. So those temperatures do change a little bit, and that's in conjunction with that thinner film. So one of the things they noted is that there's a lot of challenge to using a thin film and to maintaining consistent film thickness. You've got to have very level pans that are not warped. That might be an operational challenge. You might have to do an extra leveling step at higher temperatures, so that particularly for modified binders. So what does all of this mean as far as a potential future PG specification? The 959 research says that they're recommending Glover row parameter instead of G star times sine delta. Their research recommended keeping the same criterion, which is 5,000 kilopascals, at 10 radians a second. It's just a different parameter that you calculate. Operationally, there's really no change for the technician. You might have to have a different report out, so you might need a different script on your DSR. But operationally, there's no change. You're still doing G-star. You're still doing AASHTO T315, so it's the same procedure, still at 10 radians per second. So no real changes there. The intermediate temperatures could change if that's adopted. So you'll have to be aware of that, and that could have an effect as well. They did recommend this R value calculated from BBR data as an additional parameter for durability, and they gave some ranges there. Again, this is based on PAV20. They did some limited testing at PAV40 and had some recommendations for there as well, and the changes with the intermediate temperature. As far as 960 goes, they're recommending using delta TC as an added parameter for durability and relaxation. Anything above -2, this is again 20-hour PAV. If it's above -2, it passes. If it's below -6, it fails. If it's in between the two, then you're really going into something very similar to what is in footnote G in AASHTO M320 table 1, which basically that footnote is about using the direct tension test and failure strain, which we don't use really. At least most of us don't use it. It might be used a little bit, but basically it's a qualifier, which says, footnote G says if you're between 300 and 600 megapascals on your stiffness, you can run failure strain, and if you have above 1% failure strain in the direct tension test, you can qualify that binder at that low temperature grade. This is kind of doing the same thing. It's saying if you're between -2 and -6 on delta TC, you can qualify that binder by using ABCD and calculating that delta TF. As far as aging procedures, there's really no change in the RTFO. Again, there is an elevation change that's in the new version of T240 to pay attention to. There's no change in PAV procedure if you're keeping the same one that you've worked with. Just know that if you're going to try and simulate 40-hour PAV, you could use a thinner film. You keep the same operating parameters, but that thinner film, achieving that could be a challenge. You might use different temperatures as well. So your future specification, this is just looking at a 20-hour PAV. I don't think you're going to necessarily need to have both the R value and delta TC, or if you wanted to replace, even add in that phase angle at G star of some level, say 10 megapascals. These three parameters, R value, delta TC, at phase angle, all tell you about the same thing. They tell you about the relaxation properties of the asphalt binder. So it's not necessary to have three of them or even two of them perhaps, but right now I just put in what 959 is recommending, what 960 is recommending. I don't think these will conflict with each other for the most part. And then what this ABCD qualifier would be here, and that's just a parameter. I just defined what that line was, and that's what that delta TF min is looking at. So with that, I think I've run a little bit long, but that's all I had. I'm happy to answer any questions, and certainly if you don't have the questions answered, perhaps in your chat box, then I would say please feel free to reach out to me by email. Is usually the best way to catch me, and then I'll be happy to answer those questions going forward. I think I'm going to stop sharing here, and I haven't seen the chat box necessarily, but I think there may be a link to a survey to participate in to provide feedback. So if you would, we'd like to hear your feedback on the webinar and what you thought, and any guidance you can give, particularly as we look towards future webinars. So that should be in your chat box. Look for that link. With that, I'll turn it back over to Tim.
Okay, yeah, thank you very much, Mike. Appreciate the presentation and a lot of information to go through, but a great summary from my perspective. Looks like we've about a half hour for questions and answers. So if you have any questions, feel free to type them into the chat pod and we'll get to them. Right now, we have one question in the chat pod and a couple that came in prior to the webinar in writing. So we'll start with the chat pod. Mike, it was mentioned that delta TC did not necessarily correlate well when polymer modified asphalts were used, but does the procedure using delta TC and the ABCD better predict durability cracking for the polymer modified asphalts?
I don't know whether as far as better predicting durability cracking, I'm not sure, but what it will tell you is anytime we're doing, I guess I'll say it this way, anytime we're doing rheological testing, which is what M320 is, it's small stress, small strain. We had the direct tension test originally in the specification because that was a failure test. And we had a way of actually looking at strain to failure. We don't routinely use direct tension anymore. So what we're ended up with is looking at small stress, small strain. Polymer modified, the assumption in that is that all binders will have the same or similar strain tolerance. Polymer modified binders will have generally better strain tolerance than an unmodified material. So what that ABCD and that delta TF does is it captures that better strain tolerance. And so that's why it says, hey, if you happen to have a modified binder that looks like it's got a low delta TC, it's probably got better cracking resistance just because it handles strain better than an unmodified material. So that really was the, what captured it. And originally when we talked about delta TC, this goes back to work we did on that airfield study. We were looking just at unmodified materials. And I remember that's one of the questions we had early on was, well, what happens with modified materials? Well, they're definitely different. And I don't know that a small stress, small strain specification would necessarily capture it. So hopefully that answered the question. Maybe a little long.
Okay. No, it's fine. Very, very good. Not all the questions are always simple. The next one asks about these new recommendations and how long does it typically take to see them implemented in an AASHTO specification. So probably getting officially to the AASHTO standard specification. It's, if people want to start using these, it's probably not going to be starting tomorrow.
Right. I think we're mostly in education mode a lot with talking with the states, and really it has to be up to AASHTO if it's something that they feel like they want to implement in the specification. And that's what the research was done so that they could provide that suggestion to AASHTO Comp 2B in particular, to look at the specification to say, here are some potential changes that could address some of these issues perhaps that you're seeing. As far as how long it takes to go through that process, I think, it just has to go in. They have to decide if it's something they want to make into a standard part of M320 or M332, and then generally speaking, after it goes through the balloting process, it'll make its way through. So it still may be a while before we see any changes within M320 or M332.
Okay. And yeah, and I might mention too, AASHTO sometimes has a process they involve to help streamline that. Of course, these are the standard specifications, the M series, but then it's also possible to have the provisional standards like an MP series. So just
Right.
how we went from M320 to M332, AASHTO may want to test it out, so to speak, and see how it impacts
Right.
testing times and things like that with an MP series.
Yeah. No,
Okay.
that's a good point. And what we've tried to stress, and even in this webinar, is these are recommendations from the research. So they're not necessarily recommendations we would put forward, or we're just trying to help people understand, what did the research do, what did they find, how is it relevant to what some of these how do these proposed changes impact you and your daily operations in the laboratory. If we it would be a lot harder. I think one of the challenges we saw, for instance, in implementing or trying to implement that critical cracking temperature, which would have been table 2 in AASHTO M320, and I think table 2 in M320 still exists. But that critical cracking temperature uses the direct tension device and thermal stress analysis calculations and all that. And what it amounted to was that people that wanted to use that had to buy a new piece of equipment. The direct tension test had some challenges to it, just in how you did sample preparation and the material you're working with. And it was a potassium acetate solution. And there were just some challenges to working with it operationally. And then you had to take the data and go through this analysis procedure. And it became just kind of complicated for folks to use. And so it's harder to take off when you don't have an easy sort of adjustment. When you look at something like even a mask or test, which is AASHTO T350, it's using the DSR. It's using a little bit different script, but it's still, you load the sample the same way, you trim the sample the same way, and you just use the DSR. And so that becomes easier for people to implement. And I think the researchers kind of tried to look at that, with this, and particularly I know 959 did. And how can we get what they felt like was improvement to the specification without really burdening people by having them buy a new piece of equipment or run new tests that they didn't understand how to run and didn't have any good background on. Something like the 959 recommendation of Glover row parameter, you could run that today, and you would have to manually calculate clever row by taking G star and phase angle and doing the equation. But if enough people wanted to do it, I'm sure the DSR manufacturers would write a script that says this is how you calculate clever row in addition to G star sine delta, and it would be pretty easy for people to look at. So I think that's an important part of understanding implementation, particularly for researchers. And a lot of times researchers, and I'll put myself in that class because I do some as well, is we've got to remember how it's going to be used and how what kind of impacts is it going to have out there.
Very good. And I guess now's an appropriate time to mention a comment from Skip Paul. He says, thanks, Mike's great presentation, bringing the research together, because there is going to be that gap from research to implementation. Going back one, we have a comment here. Just make sure all graphs state that the delta TC is determined based on the 20-hour PAV. And I don't know if you have any comments there. It sounds like there's going to be some options for the long-term binder aging and how that might come together.
Yeah, I think so. Yes, they are all based on 20-hour, and I did that on purpose. They both research. If you dig into the reports, both projects will talk about 40-hour PAV as well, because at that time, I don't think they knew for sure what people were going to be doing 20 or 40 hours. 40-hour PAV is, I mean, obviously that's twice as long, so that adds to some complexity. If you choose not to do 40-hour PAV, but choose to do the thin film version of that for 20 hours, it doesn't add time, but you've still got some complexity of making sure that you've got the pan level, and there's some challenges there potentially. It's another potential source for error, I guess. One of the things that we've seen just in work that we've done is that as you progress in aging, particularly as you're doing cold temperature testing, like in BBR, when you go from 20-hour to 40-hour PAV, you're more likely to get variability. And so and I think it's because of the stiffness of the material. It's about the additional aging that's occurring. And so variability is something we didn't really talk about too much, if at all, but that's an important piece in implementation as well. It doesn't do any good for us as researchers to suggest a test for a specification that is going to have huge levels of variability, because then you're not going to know what you're going to get. So I think that's an important piece for us to have as well.
Okay, very good. Have a lot of questions coming in here, and just to let you know, Mike, and we have maybe about 15 minutes or so left, but
Okay.
here's one. If there are compatibility issues with the polymer being used in a particular binder, I would expect delta TC to not be good. Should we expect the binder to also perform poorly in the ABCD delta TF also? And if not, how do we address these compatibility concerns? Perhaps separation testing?
That's a good question. And I haven't looked at the 960 research enough to know whether they would expect that. I know one of the things that they looked at was the colloidal instability index and how that relates to what they see with delta TC. Generally, if it's colloidally less stable, you're going to have lower values of delta TC, or it's going to have poor relaxation properties. I guess my expectation would be, and this, I could be totally wrong, so I'm going to preface it by saying that, but my expectation is that if you've got a polymer modification that's not compatible with the base binder, I would not expect it to necessarily perform as well in the ABCD. I would think, you're gonna, if it's not compatible, if it's not homogeneous, I think, you're gonna create opportunities for it to crack a little bit earlier. That's my speculation, but I don't have data to support that. I'd have to defer to the 960 researchers.
Okay, well, that's a fair answer, a good starting point, and perhaps an opportunity for additional study there.
Mhm.
Next question is, some agencies have already included delta TC in their specifications, and they've set the criteria based on values reported in the NCHRP work, but are requiring the 40-hour aging as opposed to 20 hours of aging. Do you think there's going to be a different set of specifications for 40-hour aged material?
Or things like delta TC and that sort of thing? Is that what?
That's how I understand the question. Yeah.
Yeah.
So if somebody's already gone to delta TC and they want to change the aging, wonder
Yeah,
how they could
I would
proceed.
think, yeah, I would think so. I mean, I would expect, so generally speaking, I would expect delta TC to get more negative as you go to more aging. And I think, we saw that one graph where I showed where we went from unaged to PAV 20 to PAV 40 to PAV 80, even though it was black space, the way it ages, the graphs changed enough, the curves changed enough that you're expecting it to become stiffer and more brittle. And I think that'll show up in delta TC. So generally speaking, 40 hours should be more, you should have values that are lower, more negative than what they have at 20. Now, I think the original 9-60, what they proposed in phase 2, was -2 and above was okay, -6 and below was not for 20-hour PAB. And I think for 40-hour, they looked at -3 and above was okay, and -7 and below were not. So it only moved by 1 degree. I don't know that I believe that. I think it probably needs to be a little bit more than that based on aging, but it's probably going to depend on the binders that they tested and what they were looking at as far as how that moved with aging. I know I'll say this, if people were going to routinely use 40-hour PAB, I think you'll have to reevaluate just about everything that you're doing after aging, the intermediate temperature properties, the low temperature properties. It wasn't the basis behind the PG specification. So I think it becomes a much more complicated scenario.
Okay. Yep. When changing one thing, there could be complicating factors that change others as well.
Definitely.
Okay. Next up, we have, could a SERA analysis of the binder be used in combination with the BBR to improve the prediction of durability cracking? And if so, are there any particular fractions that would correlate to the durability properties of the binder?
Yeah. I know they've done SERA analysis with these materials, and I think that kind of goes back to the colloidal instability index, or I think it's got another term. I may be using the wrong term because I'm not as good with chemistry as physical testing. But generally speaking, I think what we expect to see happen is that as the binder ages, your asphaltenes they increase, and what happens with your aromatics and your resins is that they'll decrease. In some cases they'll stay about the same, but it starts to get out of balance. So that balance that you need behind taking the asphaltenes and keeping it in that matrix. And forgive me if JP or Dave Anderson or anybody like that is on and I'm explaining something poorly, but basically I think what happens is you get the material out of balance. And when that happens, then that shows up sometimes in the relaxation properties. So yeah, I do think that you could probably look into that and use SERA along with some data, and that would give you some indications. The colloidal instability index, which I'm going to hesitate to I think it's asphaltenes and saturates divided by aromatics and resins, but I may have that backwards. But that will have some relationship to the delta TC and to the relaxation properties. So that's how I think it's been used.
Okay. Well, it sounds like sometimes safeguards go into place. I remember when M320 first came out, some states kept some what we called PG plus tests. And as things change here, some states may want to safeguard here or there as well.
Right.
Here's a comment from Skip Paul that he thinks in the NCHRP 9-60, he thinks the recommendation will be 20 hours as results are not that different, just to share that with the group.
Yep.
And then next question we have, I feel like the research findings could be relevant when using binders with high percentages of RAP or RAS binders that are blended with the virgin material. For states specifying binders using M332, quantifying the unknown binder grade of the blend has proven to be difficult. Is there any research to come up with something similar to R29 used for grading an unknown under the M320 for M332 so that those states can determine the proper test temperatures?
Yeah, that is a great question, and it's something that we've talked about. I think AASHTO R29 effectively has not been touched in a number of years. I mean, I know it's been reviewed and updated, but yes, there needs to be something as we look at some of these new parameters potentially, and as we look at using M332 as well. there needs to be some more or better guidance on there. And I agree with that, that would be something that we need to take a look at. We also, one of the other questions, so for researchers that are out there and are thinking about what to do, and some folks may have already done this, one of the questions that I get periodically is, well, what happens if I've got, say, a lower delta TC? Suppose I've got like a -6 delta TC, and I also have an asphalt binder that's a -2 delta TC. Can I blend those two together like 50-50 and get a -4? That's what you would think from linear blending, but I doubt it works that way. So some of that has got to be able to provide some guidance to people on what do you do if you got a low value? If you're wanting to change it, how do you change it? What kind of things do you have some control over in order to make those changes? So, and I'm sure that suppliers have looked at this and are continuing to look at it, but that's one of those questions that I think is still out there that I don't have a good answer to. I doubt seriously it's a linear blending, but well, I'm be interested to see what it is.
Okay. Next up, here's a question that says, I've seen how refining techniques and crude sources can impact our projects. How do the proposed revisions to the PG binder specifications address the unique performance challenges under these situations?
Yeah, so I think right now, if you look at M320 and M332 in the form of the intermediate temperature cracking, because if that's what we focus on, and I think generally speaking, as far as high temperature rutting goes, I feel like we've got that pretty, I won't say well in hand because things can change in a heartbeat, but I feel like we have the right characterization tools there. So when you're looking at JNR and the masker test, and even for unmodified binders, just looking at G star divided by sine delta, I feel like that's good for our high temperature, and looking at RTFO, I think that works well. I think low temperature, even though there have definitely been some challenges with the BBR and that sort of thing. I think just looking at stiffness and M value help us with understanding low temperature cracking. But I feel like where we don't have as good a handle on is that intermediate temperature cracking. And I know some people have disliked G star times sine delta from almost the very beginning. I think it tells us some information. I think we can get some more information, and that's where understanding, that, okay, we're using some different refining processes maybe, or different materials maybe than what we've used before. There are different blend agents than maybe what we used in 1990. So what are our materials doing, and how do we characterize those, and what's the proper parameters? And I really think that's what the 959 and 960 in particular, I think that's what their research was centered around, was how do we characterize those materials? I think if we've got the binder spec set properly with whatever that may be and wherever those limits may be, then we'll realize what the intent of the specification was, which is to reduce the binder's contribution to these distresses. It's not going to fix the distresses. If you're using too low of an asphalt content on your mixes, you'll probably get cracking. If you decide not to roll the pavement, you'll probably get cracking. There are things that are going to be outside of the control of the material specifications you put in place. But I feel like if they review the specifications, if they settle on what makes sense, what parameters make sense, what limits may make sense, then I feel like then they will kind of achieve their goal of, hey, the binder specification is doing what it should be doing, that it's doing its part, so to speak.
Fair enough. We'll hope for the best there. That makes a lot of sense. Couple more questions. I think that will wrap this up, this next one is what test parameters are likely to correlate to raveling, especially raveling at higher temperatures?
Of the test parameters that I think the parameters from what 959, 960 we're looking at were the R value and the and delta TC. And as I mentioned, I think also phase angle at a modulus. So we've been using G star equal to 10 megapascal as our modulus. I think those parameters relate to relaxation, which relate to raveling. Again, they're going to relate to the durability that you're going to see. There are other parameters, obviously, that'll lead to raveling potentially, but those are kind of the ones that the research focused in on.
Okay. And I think we'll have time for just one last question here. And this discusses these proposals, or this new specification is based on refined binders or refined blended binders. And what's the feeling about these new tests and new recommended specifications regarding the introduction of alternative chemistries like recycling agents or rejuvenators?
Yeah, I think some of the recommendations that we've seen are intended to help capture that. One of the things that, you know, as you're adding in products, you know, you're going to change the chemistry potentially of the binder depending on what you're adding, and that could change its behavior, its relaxation behavior, and how it oxidizes, and all those things can have an impact on what it's going to look like and what the performance is going to be. So I think they're good tools for us to be able to use and evaluate, you know, right now what we're seeing. I don't know how they're going to work within the specifications, but I do think that some of the tools that were offered here through the 959 and 960 research and ongoing research, I think are useful to help us hopefully evaluate those types of materials.
Very good. Well, Mike, certainly appreciate your presentation and all the information. Sounds like it was very helpful and informative with all the questions we got. We'll look forward to some future developments as well. I'd also like to thank all the participants for attending and asking all the questions. I think the questions help bring clarification to the next directions as well.
Yeah.
So we'll have
if I could, Tim,
sure.
just a reminder to folks about the survey that was in the link, and I asked them if they could provide feedback. We would certainly appreciate that. Thank you.
Sure, you bet. And so with that, I'd like to conclude or close out today's webinar. And we don't have one set for 2 months for now, but that's in the works. And hopefully we'll be in touch at that time with the next webinar. So thanks everybody, and have a good rest of the day. Okay, so bye now.
Thanks.